Special Theory of Relativity. Lecture 3. Energy and Momentum of a Relativistic Body. Part 1. Energy of a relativistic body. At high speeds, not only temporal and spatial intervals and mass change, but also the energy of the body. The very relationship between the energy and the velocity of the body changes. It turns out that kinetic energy is determined not directly by the velocity of the body, but only by the mass of the body. The relationship between energy and mass is given by Einstein's well-known formula: energy is equal to the product of the mass of the body and the square of the speed of light. The following new consequences follow from this formula. First, energy is actually proportional not to the square of the velocity of the body, but to the mass of the body. The proportionality coefficient is the speed of light, or more precisely, its square. Consequently, the increase in energy with increasing velocity is explained not by the increase in velocity itself, but by the increase in mass with increasing velocity. Secondly, at zero velocity, the energy is not zero at all, as in classical mechanics. It is equal to the product of the rest mass and the speed of light, and is called the rest energy of the body. This inequality of zero energy at rest is obviously due to the inequality of zero mass at rest. Part 2. The essence of the kinetic energy of a non-relativistic body. As can be seen, at low velocities, the energy of a body is approximately equal to a constant product of the speed of light squared and the rest mass of the body, i.e., the rest energy of the body. A small deviation of the energy of a moving non-relativistic body from this constant, i.e., from the rest energy, is the kinetic energy that is included in all formulas of classical mechanics. The rest of the body's energy, which is a constant in classical mechanics, is simply not taken into account, since the energy of a body is defined only up to a constant. Note that classical kinetic energy, as a small correction to the relativistic energy of a body, is obtained by expanding the relativistic energy in a Taylor series in terms of a small ratio of the body's velocity to the speed of light, and restricting ourselves to the first two terms of this expansion. The first term of the expansion is the rest energy, and the second is the ordinary kinetic energy of the body. Thus, the very presence of kinetic energy in a body is a relativistic effect, namely, a consequence of the dependence of the body's mass on velocity. The fact that this relativistic effect, unlike other relativistic effects, manifests itself even in non-relativistic bodies, is due to the presence of the square of the speed of light in the formula for energy. Since the speed of light is very large, relativistic effects associated with energy are greatly amplified, thus becoming significant even in non-relativistic bodies. Part 3. Momentum of a relativistic body, and the relativistic relationship between energy and momentum. As for momentum, unlike energy, its formula in relativistic mechanics remains unchanged. In the relativistic case, momentum is still equal to the product of mass and velocity. And since the formula for energy in relativistic mechanics is different, the relationship between energy and momentum will also be different. That is, energy can no longer be represented as half the product of momentum and velocity. The energy and momentum of a body will now be related as follows: momentum is equal to energy multiplied by the ratio of the body's velocity to the square of the speed of light. Part 4. Energy and momentum of massless bodies. For massless bodies moving at the speed of light, the formulas for energy and momentum discussed above are not applicable. Since, obviously, in the case of zero rest mass, these formulas yield zero values for energy and momentum.